let's get started. It's 9 o'clock, and so today we have a very special visitor from UCSD, and Dr. Riera was supposed to be the host, but he has a medical appointment, so he asked me to step in to introduce the speaker. I happen to be following his research work closely over the past few years, and we see something pretty impressive. Okay, so Dr. Sheng is a full professor in the Department of Chemical and Nano Engineering at University of California, San Diego. And Dr. Wu got his bachelor degree in chemistry and molecular engineering from Beijing University in 2006. And after that, he went to Georgia Tech and did his PhD in materials science and engineering in 2010. And I want to say that he was a recipient of 2011 IUPAC Prize for Young Chemists for his PhD research on oxide nanowire arrays for energy science. And after the PhD study, Dr. Wu went to became the postdoc research associate in Fractured Science Material Research Laboratory from 2011 to 2015 at University of Illinois at Champaign, and where he started developing advanced wearable electronic systems for healthcare and energy applications. So Dr. Wu's research interests focus on understanding the electrical, mechanical, and other characteristic behavior of the functional inorganic materials when they are geometrically engineered into a soft form. And exploring these materials as a building blocks for soft electronics, nano electronics, and engineering harvesting storage devices. So today, Dr. Wu is going to showcase his research on wearable ultrasound technology, and I think you will be impressed. And please join me in welcome Dr. Wu.
Thank you so much, Dr. Lin, for the warm, kind introduction. And I can tell these introductions were prepared and made by you because I did not provide this material to you. Thank you so much. And good morning, everyone, for attending my seminar. It's such a great honor to be here. As Dr. Lin mentioned, my research is on this wearable ultrasound technology. What does that mean? So I have quite a few examples to illustrate the potential and advances of this technology. So wearables, right? So I'm sure you heard lots of news media stories and seen lots of papers on wearables. So why do we need wearables? So this is the scenario when a patient in the hospital is connected by many wires for measurements and diagnosis, all kinds. And obviously those wires are very, very cumbersome, inconvenient, and requires lots of nurses, physician assistants time to connect them, to disconnect them. And this type of measurement is only available in the hospital. When the patients leave the hospital, doctors have no idea what's going on, so they lose lots of data. They may miss some critical moments that can illustrate the disease development. So sometimes when the patient is critically ill, then those doctors will have to order invasive procedures, such as surgery, blood drawing, so on and so forth. I would say the holy grail of this community is to come up with a device like this. So this device is flexible, stretchable, can be laminated on the human skin without constraining your daily activities. You can walk them to anywhere you want and do this monitoring 24/7, so it's continuous. You do not miss any critical information at all. And most importantly, this device will be able to access your deep tissues, central organs, even without breaking your skin. So this is the holy grail. What you're looking at here is a video showing a device that we demonstrated about 10 years ago. So in this case, this patch is laminated on the human chest, and it's taking a coil to deliver power. And when this device is powered up, it can wirelessly collect your EKG signal, heart rate, and transmit those data to the cloud, cell phone, doctor's office, so on and so forth. What you're looking at here is the raw signal we were able to collect. And in this video, you can see those high quality EKG waveforms, right? You can identify those PQRST characteristic peaks as you would expect to see in those hospital measurements. The baseline is drifted because it's a capacitor in the circuit, so you have to charge up the capacitor before everything becomes stable. So if you do a deep dive in this wearable community, you will find out that there are so many advances, so many emerging technologies of wearables. No matter is commercial products, some of you may wear Apple Watch, Fitbit, Garmin, maybe something like Samsung, wristband, or academic prototypes you read from those journal papers, right? They can measure so many things, so many signals. Sometimes you get lost what they can measure. Right? There are lots of similarities and overlaps. So here are like a few signals you can measure to basically highlight, such as breathing, EXG, ECG, EMG, EEG, ECG, so on and so forth, so on and so forth. I'm not going to go through each one of them because they are not my focus. Here my focus is those signals existing wearables can measure have a common denominator. They are limited to the skin surface or shallow tissues. Some of you may wear Apple Watch. On the back side of the device, there's a blinking LED. Sometimes it's green, red, infrared, and depending on the transmission mode, it measures your pulse ox, your your oxygen saturation levels, right? So those light sources can only penetrate a few millimeters beyond the skin surface. So on the way here, Dr. Lin and I were discussing about these challenges of these optical sensing approaches. So however, there are a lot of more exciting things beyond a few millimeters below the skin surface. In your heart, in your lung, in your kidney, in your musculoskeleton, in your brain, so on and so forth, right? Then the question boils down to how can you access those deep tissues, central organs, on a non-invasive, wearable platform continuously, right? So we eventually thought about ultrasound. Why ultrasound? A few reasons. Ultrasound, first, it can penetrate human tissue as if we see through glass. It's transparent. It can penetrate as deep as 17 centimeters. At least in our lab, we demonstrate. So that's very, very deep, right? For a Asian male like myself, 17 centimeters, it can access almost every part of the human body, right? Second thing is ultrasound is used widely in hospitals. You can almost find ultrasound in every division of the hospital. So it is very functional, a lot of things you can leverage. Third, it has been used for over half a century, so it has a proven track record of biocompatibility, so it's very safe. So by integrating ultrasound on this wearable platform, we can start to monitor, track those central organs, deep tissues, non-invasive continuously. So ultrasound opened up a new sensing dimension for this existing wearable community. So this is like a very exciting area. A lot of things you can look into. I should just showcase a few examples. So what you're looking at here is the schematic of this wearable ultrasound patch that we published about 6 years ago. In this case, there are like 100 transducers, 10 by 10 array. And each one of the transducers is individually connected, addressed to transmit and receive ultrasound. And on the right here is explored the view of a single transducer. So it's multi-layered to maximize the performance of each transducer, so that you can transmit more ultrasound in the human body and receive the highest signal-to-noise ratio of these echoes from the human body. And one unique structure of this piezoelectric transducer we used is so-called a 1-3 composite. It's basically those piezoelectric single crystal material embedded in a 2-dimensional polymer matrix, so that those vibration along the longitudinal direction is enhanced and the lateral shear vibration is suppressed, so they get more ultrasound transmitted in the human body. And at the bottom here, those images showing how soft this device is. It's flexible, stretchable, and it can be twisted, showcasing the mechanical compliance of this device. So what do we do with this wearable ultrasound device, right? So we first thought about the NDE, non-destructive examination. So this is a whole field by itself. It's basically a technique to detect those defects, those fatigue in infrastructure components, right? And some of you may heard of those airplane crashing and engine explosion during flights. So why don't they discover those metal fatigue defects in those engine components before the flight took off? That's because for those sophisticated infrastructure components, it's so curved surface and lots of small cavities. Conventionally, they will have to disassemble everything and immerse those sophisticated components in liquid environment so they can do those imaging, right? So here in this case, we can do this in situ imaging on this non-planar surface without disassemble everything. So this is schematic showing that on a this sinusoidal surface, there are like two embedded defects, and with this soft ultrasound patch, we can do 3D imaging just in one shot. So this 3D image result in 3D, this image result in 2D along different directions. I would say the most exciting potential of this technology is to apply them to human body to solve biomedical problems. And what are the biomedical problems we thought about, right? And the first thing we looked at was like hypertension. Hypertension is the #1 risk factor for cardiovascular disease, which kill more people than all cancers combined. So this is the operational scenario showing how we can measure blood pressure. So this is the patch on the neck, and there are two critical vessels we are interested in. One is called the carotid artery, blood flows into the brain, and the other one is called the jugular vein, so blood comes out from the brain, right? And this is the mechanism showing how we can measure blood pressure using ultrasound. So imagine there is a transducer lay on over this vessel, and it emits a ultrasound beam. This ultrasound beam will be reflected by those two vessel walls. Because of this acoustic impedance mismatch, right? Solid, liquid, liquid, solid. So there's a mismatch, so the ultrasound will be reflected most strongly at those two interfaces. And as you can imagine, when this blood pressure pulse comes in, your vessel will actually dilate, collapse, right? And then that means what? That means those two peaks will shift back and forth during this vessel pulsation. And by monitoring the distance between those two peaks, you are measuring vessel diameter. And through a series of well-established equation and calibration, you can convert vessel diameter to blood pressure. Basically, the higher the blood pressure, the larger the vessel diameter. And we can transmit 5,000 pulses of ultrasound per second into the human body. That means what? We can measure blood pressure 5,000 times every second. They may ask, hey, why do we have to measure blood pressure so frequently? I don't know. So that's the question. I'm posing here to this biomedical engineering audience. So we showcase this technology, this capability here, and this is blood pressure waveform. It's like as I just said, 5,000 data points every second. You can identify lots of interesting features. You can potentially make sense out of. One advantage of this wearable ultrasound patch is it can achieve intimate conformal contact with the skin surface, even without gel. So this is the patch on the skin. It can achieve intimate lamination, and you can see the blood pressure waveform with gel, without gel. They have similar quality because this material, this device, is packaged by this silicone elastomer that have similar acoustic impedance with the human skin. A lot of people are asking this question. You will need calibration to convert vessel diameter to blood pressure. How often you have to recalibrate because of those physiological parameters changes, right? And how long per each calibration last? I got asked about this question a lot. And in our just accepted paper, we showed that this calibration can be held for at least 1 year. So this is the data measured on 4 healthy graduate students. So you can see here, on day 1, we calibrated, and then do those comparison measurement between the ultrasound sensor and the cuff once a day for the first week, once per week for the first half a year, and once per month for the second half a year. As you can see here, the measurement between the ultrasound and the cuff match to each other very well. and the discrepancy between that is less than, on average, 5 millimeter mercury. That is under this FDA regulation. So that's for healthy graduate student. How about for patients who have those very, very unstable hemodynamic status and may have those drugs that they can affect those physiological status, right? So we compared the ultrasound sensor with A-line for those patients after cardiovascular surgery in the ICU, continuously compare them for 12 hours for patient 1 and 10 hours for patient 2. And you can see here, those measurements between those two modalities match to each other very well. The trends, everything, and also the details have been analyzed by those vivid spectrum coherent analysis. You can see those modalities match to each other very well. So those are just 2 patients. Here in this paper, actually we show 4 patients, and we only measured 4 patients, which is not like we measured 10 or 20 patients and we picked 2 or 4 and published it. No, we just measured 4, and all of them show those show those high correspondence between those 2 sensor modalities. So wearable ultrasound that allows you to do more frequent monitoring at home, right? So this is the validation of these subjects, 7 subjects, when they perform different activities, 13 of them at home. And we compared those measurements between the ultrasound sensor and the cuff when they do all kinds of different activities. You can see here, those activities change the blood pressure, waveform, morphology, baseline, heart rate, values, everything as what we expected. So when you compare those readings between the ultrasound measurement and the cuff measurement, you can see that ideally those data points should fall on this diagonal dashed line. This is the ideal case, perfect case. But in reality, those data points fall within plus or minus 5 millimercury difference between each other, and that is under this FDA regulation. So this is the systolic blood pressure, mean arterial pressure. We can also do the same thing for the diastolic blood pressure. So ultrasound can do lots of modalities, and one modality is called the A mode. It's basically you have a transducer and you can emit ultrasound wave in the human body, and all those tissue interfaces will reflect ultrasound wave and it gets eventually picked up by the same transducer, right? So we use this A mode from a single transducer to do human-machine interface to control robotics, control prosthetics, so on and so forth. So how does that work? So you can imagine this your finger joints, your hand gesture, are all controlled by these muscle groups, right? That means what? One particular muscle group distribution corresponds to one hand gesture, right? If you change your gesture a little bit, your muscle group distribution will also change correspondingly, right? So you can imagine this, right? So if you put a transducer on top of your forearm and you emit ultrasound wave, as I just said, those tissue interfaces will reflect the ultrasound wave and eventually get picked up by the same transducer, and that is called this A mode, radio frequency signal. A mode is the entry, right? This is an A mode signal. Each data point on this A mode signal corresponds to those reflections from all those tissue interfaces. That means one simple A mode signal contains all information about your tissue muscle distribution, right? And how do you decode this A mode signal? How do you correspond this A mode signal to this muscle tissue interface? It's almost impossible to do this using mathematically, but here we are at the age of AI. So this postdoc, he basically built up this neural network, convolutional neural network, to build this one-to-one correspondence between this A mode signal and the hand gesture. Eventually, we were able to do this prediction with very high accuracy. So this is the demonstration showing that we fixed all other joints, angles of your hand, and just bend your middle finger. You can see those A mode signals, those peaks evolve, and some of the new peaks show up, and old peaks disappear, so on and so forth. So this is the bending middle finger. We can do the same thing for the wrist, right? Keep all the finger joints the same, just rotate your wrist, right? You can see those peaks evolve in the A mode signal as what we just expected. And by this convolutional neural network, we can build this correspondence, and we can do similar things. some index, middle, ring, so on and so forth, right? And you can see the ground truth and the prediction matches very well. So that shows that using a single transducer AMOR signal allows you to capture all those critical information about your muscle distribution, and that empowers you to build those human-machine interface. And a lot of people will ask you, will ask this question. Muscle activity can also be measured by EMG, right? Electromyogram. What's the advantage of ultrasound compared with EMG? I would say 3 advantages. First, stability. As you can see here, EMG has a lot of noises like this, peaks, right? This is actually not noise. It's actually those random neuron muscular fiber firing, and it's not very stable at all. It's because you cannot control it. How ultrasound is very stable because if you do not move it, if your muscle is static, the ultrasound peak is stable, right? So anything that is moving means your muscle is actually moving. So it's actually very stable. Second, that EMG is has a lack of this spatial resolution, because if you put a electrode on the skin, EMG is collecting coming from everywhere, and the electricity speed is very, very fast. You cannot have any like a time of flight measurement tell where this EMG signal is from. But for ultrasound, it has this time of flight. You can pinpoint which muscle fiber is actually moving, right? And the third thing is EMG has a small signal to noise ratio. You really have to make a strong face because before you can detect meaningful EMG signal. However, ultrasound is very, very sensitive. You just move your finger a little bit tiny, you can see those peaks shift, very sensitive, right? So those are the 3 advantages. Ultrasound is a very, very powerful technology, and I just love this technology so much that you can learn from this literature by integrating those ultrasound technology with a wearable platform. And one powerful technique is so-called phase array. If you do not know what it is, it's basically a technique to control the focus and steer the ultrasound beam by timing the activation of each transducer element in the array. So how do you know this phase array is behaving in the human body? Human body is mostly like 50 or 60% of water, so we do characterization in water before we apply them to the human body. Right? So this is the water tank showing that we can do this characterization of ultrasound behavior before we apply them to the human body. Right? So this is the patch on the water surface, and you use the hydrophone. Hydrophone is an ultrasound sensor that can tell how strong the ultrasound intensity is. And this hydrophone is mounted on a 3D motor that you can do the 3D mapping, right? And this is mapping result. You can see, this is wearable. This is the patch, and you can focus and steer and emit the ultrasound beam in the water and penetrate as deep as 17 centimeters. So the cross section of the ultrasound beam is as small as like a few millimeters, and of course this is tunable by the ultrasound frequency, the transducer structure, and also the penetration depth. So this is the GIF image showing that we can do scanning of ultrasound beam in the water tank and in the human body as well. So this is the patch position by timing the sequence of this activation of each transducer element. You can actually steer and rotate the ultrasound beam in the human body, right? This gives this wearable a new degree of freedom. What does that mean? For conventional wearables, say for Apple Watch, if you want to measure something at one location, you have to move this device to this location. And if you change your mind, you have to remove this device and put it on a new location, right? So this is like a passive collection. But for ultrasound, you can do 3D active scanning in a 3D volumetric space, and then use this data, this AI-based data analysis to pick the region of interest, and then do those active searching or sensing, right? So this is the experimental result. This is the simulation showing the close matching with each other. And I'm sure Dr. Lin will have this question that for phase array, you will have those timing of activation. If your transducer array is flexible, stretchable, you do not know the transducer location, right? How do you know the transducer location before you apply this time of activation to each transducer element, right? I'm telling you, this is a grand challenge for this wearable ultrasound community, and lots of people are trying to tackle this challenge. I would say there are over 10 papers published already, but those papers have their pros and cons. before people find out a really ideal solution for this, we find a way to detour it. Our way of detouring this problem is to use low frequency. Why low frequency? Because low frequency has long wavelengths. Long wavelengths is less sensitive to those transducer location change. So how does that work? So this is the schematics showing the principle. Imagine if you have a transducer that is flat on the planar surface. In order to focus here, the blue bar is the time delay profile, right? Delay profile means this one is activated first, this one is activated last in order to focus somewhere here, right? So this is on a planar surface. For the same transducer array, if it's on a curved, bended surface with a curvature radius of 4 centimeters. 4 centimeters is very, very small. It's like this much, right? Bend this much, smaller than my neck, right? For such a small bending curvature, in order to focus at the same spot, the yellow bar is so-called phase separation correction you have to add on top of this blue bar. As you can see here, this yellow bar is on average 5% of this blue bar, so it's very, very small. In other words, you can safely ignore this yellow bar and just directly apply this blue bar. It will probably work as well as you apply it. So that's the hypothesis, and this is the experimental result. The transducer patch is here. It's on the planar surface. You apply certain time delay profile. It will focus and tilt the beam with an angle of 15 degrees. This is on the planar surface. When the same transducer array applied on a curved surface with a curvature radius of 4 centimeters, that's very small. You applied exactly the same time delay profile as if it's on the planar surface. You can see it's focused and tilted with the same angle, with slightly reduced intensity. That means what? We can safely ignore this bending curvature change. Just treat it as if it's on a planar surface. Why we can do this? Because we use low frequency, 2 megahertz for this case. Low frequency has long wavelengths. Long wavelengths is less sensitive to this bending curvature change. So with that in mind, we can use this phase array to do lots of interesting things. For example, flow monitor, blood flow monitor hemodynamics. Why flow? And I'm sure for this biomedical engineering audience, you will appreciate that the human body is so complex. But if you simplify it, say, hey, the heart is the battery, then the blood pressure is the voltage and flow is the current. Vessel resistance is the resist, right? So in order to understand the human circuit, you have to know both blood pressure and blood flow. So the same thing, we apply the phase array in the neck and monitor these 2 vessels that are my favorite, carotid and the jugular vein. You can see this is the color Doppler image of the carotid. We can do the same thing for the jugular vein. This is a 2D image, cross-section. And after you know this beam direction and the vessel direction, you can calculate the blood flow velocity without any calibration. So this is a spectrum Doppler. You can identify the end diastolic velocity, peak systolic velocity from the patch, from the commercial device. And we have done Bland-Altman analysis to show the high correlation between them. And lots of people ask me, can your wearable patch measure signals behind the bone? In other words, can you measure hemodynamics in your brain, right, behind your skull? And I'm sure you can agree with me that the bones strongly reflect the ultrasonic signal, and that reduces your signal-to-noise ratio. So this student, he basically self-studied. He learned this amazing technique called ultra-fast imaging from the literature. And that allowed us to do this 3D mapping of these cerebral arteries in the brain, in the brain through this temporal window. And if you do not know what it is, this ultra-fast imaging, I did not know this until I learned this from him. So basically, it's a technique that allows you to transmit hundreds, thousands of ultrasonic pulses every second. So you get lots of signals, and you can superimpose, accumulate those signals together, so you can do averaging and eventually significantly enhance this signal-to-noise ratio, and eventually get this 3D blood vessel mapping called the circle villus. So this is the mapping result of your circle villus. So you can identify those major artery branches, right? I'm not going to go through each one of them. This is the 3D view, interval orientation. And we can also record these spectrum Doppler flow velocities, flow profiles from each major arteries, right? Anterior cerebral artery, ophthalmic artery, middle cerebral artery, so on and so forth, right? And those are, those waveform morphologies match our expectations very well. And we have done some maneuvering to show that this can be mapping can be achieved in real time. So as you probably can agree with me that this carotid artery is where the blood flow flows from the heart to the brain, right? And your circumvallus, this cerebral artery, is symmetric from the left and the right. But if you compress it, if you compress this left carotid artery, that means your flow to the brain on the left side will reduce, as reflected by these thinner arrows here, right, on the left side. So your body, after millions of years of evolution, will have this automatic compensation mechanism. So on the right-hand side will increase just by itself. So you can see these arrows become thicker, right? So this is auto-regulation. And most interestingly, we apply this technique to continuously monitor the subject for several hours. And during this measurement, the subject becomes drowsy, sleepy, and we observe this very interesting phenomenon. You can see there's a peak systolic velocity in the middle cerebral artery have this oscillation at a frequency of about 0.1 hertz. And this is called a B wave. It's a very, very active neurovascular coupling mechanism that people are researching, and it's associated with those memory consolidation, lymphatic flow, and removing this toxic metabolites from the brain. So this shows that our technique can provide those accurate and feedback for those real-time measurements. I would say ultrasound is most valuable for this B-mode imaging. And for cardiologists, so those are the 4 common modalities they use to diagnose your heart, including apical 4-chamber view, apical 2-chamber view, peristernal long axis, peristernal short axis views. So this is the schematic showing this cardiac anatomy and imaging orientation. So this is imaging result from the wearable patch, imaging result from the clinical device. You can see the close quality between them. So what I want you to notice is that you can imagine when you move this cross section along this direction, right? Along this direction, you got these different cross sections with your heart, so-called basal view, mid-cavity view, and apical cavity view. If you superimpose all those views together, you got this so-called 17-segment model. With each segment corresponds to one area in your myocardium, right? With your heart muscle. And why is this interesting? So by monitoring the beating behavior of each segment on this 70-second model, you know which part of your myocardium has the so-called regional wall motion abnormalities. Right? I'm learning this medical terminology from my students. Why is this important? There have been clinical evidence to show that regional wall motion abnormality is about half an hour earlier than conventional EKG to predict heart attack. And I'm sure you know, heart attack is very acute. My father actually died of a heart attack. Within 2 hours, he just passed away. So by knowing this heart attack 2 hours beforehand, you can potentially save lots of lives. So this is the video showing my student is doing this imaging in real time in the lab. You can see for this wearable ultrasound patch, in this case, it has 2 linear arrays that can provide you 2 orthogonal views of your heart. And those 2 views are simultaneous, complementary to each other. And on the display, they have those 2 different structures. You can identify those interesting cardiac anatomy. And what I want you to notice is when the student put the patch on his chest, he starts to do some exercise, start to move around. And you will notice that this ultrasound imaging quality is not affected at all, right? There's no motion artifacts. You can see this imaging is not like compromised at all. So that enables you to do imaging during exercise, during motion. Why is this important? Because some cardiovascular disease risks will not show up until you put the maximum stress, exertion on your cardiovascular system, right? right? This is why people do the so-called stress echo, right? Stress echocardiogram. And I have done this myself. I've done this in the hospital myself. In the clinics right now, doctors can only image your heart before and after exercise. So what they do is they ask you to work out on the treadmill as long as you can until you get exhausted. And then they put a bed beside the treadmill and ask you to jump from the treadmill to the bed immediately. And you lay down nicely, and then they inject the bubble and then find the right angle to image your heart. And after all those things, probably half a minute, 20 seconds have passed. Within this 20 seconds or half a minute, your heart has already slowed down. Some of those cardiovascular risks have already been, I'm not sure, have already been hidden, right? Have already been covered already. So with this technology, we can do this imaging of your heart in real time, continuously, right? Before, during, and after exercise, right? So this is the B mode imaging. This is the extracted M mode images, and this is the zoom in view of this M mode image. You see, some of the signals look like noise, but they are each one of the features. If you zoom in, to corresponding to those valve opening, closing, heart beating, breathing, lots of signals you can potentially extract. Continuous imaging produces lots of data. If you share all those data with doctors, they will be overwhelmed and say, hey, what I'm supposed to do with them, right? So we developed a machine learning algorithm to automatically process those signals, extract those actionable information so that those clinicians can act upon. So in this case, we use this FCN32 to extract this left ventricle volume from this apical four-chamber view. And from this left ventricle volume, we can derive stroke volume, cardiac output, and ejection fraction. So those three cardiac indexes tells how much blood your heart is pumping every beat, every minute, how much blood is left behind. So it's a direct measurement, direct imaging. It's not estimation at all. It's direct imaging of your heart function. And this is the left ventricle volume waveform, lots of data. If you zoom in those three critical moments, you can see the waveform morphology is very different. Right after exercise, you can see the waveform is very triangular, heartbeat is very fast. After a few minutes, you can see your heart rate slows down, and you start to see this diagonal notch because the heart have more time to complete all those processes. So from this left ventricle volume waveform, you can derive ejection fraction, stroke volume, cardiac output, heart rate. You know what? Those waveforms are very, very, critical, valuable. Why do I say this? Because in the hospital right now, they will have to rely on invasive procedures to get it. It's called the Swan and Caster. And they can only measure one number every heartbeat based on thermal dilution. And my student corrected me and said, hey, it can measure less than one number every heartbeat because the thermal dilution needs time to make it stable, right? But in any case, my key point is this technique allows you to measure 30 numbers every heartbeat, and this is totally non-invasive. So this brings lots of value to the clinical community. Ultrasound is a mechanical wave, so you can measure mechanical properties of human tissue, biomechanics, right? And mechanical properties of the human tissue is related to lots of diseases, such as cancer, cardiovascular disease, aging, fibrosis, so on and so forth. It's a whole field pioneered by the UCSD professor Y.C. Feng. So in this case, we can integrate this elastography on this wearable platform. So we use a special technique called the compressive elastography. So how does that work? So for a single transducer, you can emit ultrasound beam, and as you can imagine, each interface of the tissue will reflect a peak, right? We will reflect this ultrasound and generate a peak in this echo, right? And we'll compress this entire tissue. Some of the tissue will be compressed more if they are soft. Some of the tissues will compress less if they are rigid. Then that means those peaks will shift back and forth with different magnitude. So by correlating those two signals, this signal before and after this compression, you know which layer of tissue is soft, which layer of tissue is rigid, right? So this is one transducer, and you have a 2D array. That means you can do 3D mapping of this tissue stiffness. And this is a mechanism. And the student did a simple demo in the lab by flying this stick on a hot plate. You can see when the stick gets heated, it will dehydrate. When dehydrate, it becomes stiffer. And as time goes by, the stiff part at the bottom actually grows. The interface actually gradually moves up. How do you know your measurements are accurate, right? So we compared the measurement results from the wearable ultrasound and the conventional magnetic resonance elastography. This is like millions of dollar equipment. You can see the measurement, the mapping result in 3D match to each other very well. You can see the distribution, the anatomy structure, and also the numbers are so close to each other. They have some discrepancy because after all, those are two different modalities and they have different boundary conditions, different frequency of radiation, so on and so forth. And we also apply them to the human body, to those human body parts were prone to those muscular injury, such as shoulder, forearm, thigh, and the calf. You can see this B-mode imaging along the depths. This is the elastography measurement of the tissue stiffness along the depths. You can have a very good correlation between those two modalities. So ultrasound is a physical wave. It can measure pressure, measure flow, measure the tissue stiffness, form images, so on and so forth. How about chemicals, right? Lots of molecules, reactions in the human body. How do you extract those chemical information from the deep tissues on a wearable platform? And Dr. Lin and I were discussing about the photoacoustic this morning. So this is a wearable photoacoustic technology. So if you do not know what it is, it's basically a technique coupling light absorption and ultrasound imaging. So you can imagine when you emit light in the human body, right? Those molecules will absorb the light. Then those molecules will be heated up. When they heat it up, they will swell. When they swell, they will emit ultrasound. And this ultrasound will transmit back to the surface and eventually captured by the transducers to form images. By using different wavelengths of the light, you can excite different molecules. So therefore, you can image those molecules different, right? So this is basically a concept of this photoacoustic imaging. And here are these images of the photoacoustic patch. Yellow squares are actually the light source. We use laser. It's called a Wexel, vertical cavity surface emitting laser. Why do we use laser? Because it has strong light intensity. It can penetrate about 2 centimeters below the skin surface, right? So those are the ultrasound transducers, the same as what you just seen before. And this device is flexible, stretchable, and it can be twisted, showing the mechanical reliability. And this is the thermal camera image showing how the device is deforming during operation, stretching, bending, and twisting. Why do we use a thermal camera? Because the light source we use is 850 nanometer. It's infrared. And why do we use this infrared light? Because infrared light allows us to differentiate those 5 different chemicals: blood, fat, milk, plasma, and water, right? So this is the conventional B-mode imaging of those 5 different liquids. You cannot really tell them apart because the liquids have a similar acoustic impedance with each other. But with a photoacoustic imaging, you can clearly tell blood from the rest of these 4 liquids. Why is this important? Breast cancer is now the most common type of cancer in the US. 1 in 8 women will eventually experience breast cancer sooner or later in their lifetime. But the good thing is breast cancer is highly treatable and preventable if discovered early, right? So if you find blood in this human breast cyst, it's a strong biomarker for breast cancer. So using this technology, we can empower the patients to do more frequent diagnosis, screening, monitoring at home without the frequent visit to the hospitals, encouraging early discovery and better outcomes. So it turns out that the photoacoustic signals are linearly proportional to the temperature. So this is not our discovery. People have already find this, in the literature. So this allows us to do 3D imaging of core body temperature. Why is this important? So skin temperature is a vital sign, right? But it's very susceptible to lots of confounding factors, such as room temperature, sweating, those type of things, right? So core body temperature is much more stable is more accurate reflection of lots of physiological statuses such as inflammation and perfusion and cancer growth, so on and so forth. So this is the Fenton experiment showing that we can do a 3D imaging of this temperature in this gradient region, warm, cold. Here is the temperature gradient, right? And after some time, you can see the gradient become more uniform. We inserted two thermocouples at those two locations. You can see the thermocouple reading matches with the photoacoustic readings variable, including those trains. Thermocouples are invasive and you can only measure 2 points. This photoacoustic imaging is non-invasive and you can do this 3D mapping, right? So there are lots of more information we can leverage. So wearable patch is very useful, valuable. How do you deliver power? How do you transfer data, right? So we recently come up with this circuit that allows us to wirelessly transmit those ultrasound data to a back-end receiver with a working distance of about 10 meters. And the circuit is low form factor. It has a size of about 1 credit card, and it also has a low power consumption. So some size lithium polymer battery can power this entire system for about 3 hours. And of course, this time can be expanded. This lifetime of the battery can be expanded by optimizing the duty cycles and the performance of the circuit. One challenge of this wearable ultrasound imaging or sensing is, you can imagine, when you put this patch on any part of the body, and when you move around, your target, your deep tissue target, will actually shift. That's because of the distance between your sensor and your target, right? You move around, everything will be displaced. And in this case, when the student put this patch on his neck, when he rotated his head, you can see the carotid artery is actually displaced, quite a bit. This is very subject dependent. In his case, it displaced about 1 to 2 centimeters. And only when this carotid artery is directly underneath the patch can you get this blood pressure waveform. And then when you rotate your head, this carotid artery shifted away, you can only get this tissue interface noises, right? So this is like a moving target we are checking. So to overcome this challenge, we come up with this AI algorithm based on VGG13, so that we can analyze the signals and eventually pick the best channel, output these continuous signals automatically by itself. So in this case, there's an array of 32 transducer elements. At any time, there is one transducer that is directly on top of this vessel, right, on top of this target. And the AI algorithm can scan through this entire array of 32 transducers and pick the best channel, and eventually stitch those signals together by itself and output those continuous blood pressure waveform, even during this motion. So the student did a demo when he put this patch on his neck, and he ride a bike and do all kinds of hand motion to trying to displace his carotid artery, and this is the data he was able to measure. So you can see at the top, those 3 curves of the IMU showing this head motion. In the middle is the blood pressure waveform continuously, right? And at the bottom is the heart rate waveform. You can see during those 4 critical moments, that's when he was doing this head gesture, displacing his carotid artery. You can see during this head motion, the blood pressure waveform is not interrupted. It's all continuous. Well, ultrasound is so mature. Lots of big companies, lots of products out there already. The most advanced ultrasound technology is called the POCUS, point of care ultrasound. And people can put them in the pocket and walk anywhere they want, right? So people ask me this question: how does your technology compare with the POCUS? What are the value-added benefits of the technology, right? So I would say POCUS is so functional, but it still has 3 critical limitations. First, it has to be manually applied. And the clinicians will have to scan different locations, different angle, and apply different pressure, right, to get the best result. That creates a significant challenge of ultrasound. It's called the operator dependency, because the user has to be very experienced, has to be very well trained. Otherwise, you get different results and sometimes even wrong results. And because it requires a very experienced user, so this technique is very expensive. It's not a problem for the US, but for those low middle income countries, or for those people living in a remote area, one ultrasonographer is taking care of 200 patients simultaneously. And second, this technique is still limited to one-time testing. It's normally taking place in the hospital only, and it gives you only a snapshot of what's going on. There's a lot of information. And most importantly, is the patient has to remain stationary, cannot move around. And then last, this technique requires gel, which creates a problem for disinfection if you want to use this device across different subjects. So for this wearable patch, you just have to slap it on any part of the body you want to monitor. This 3D phase array scanning monitoring will get the volume of these images from the human body. And the AI-based data processing will extract those signals automatically by itself. So it does not need this user to be well-trained, to be experienced. It empowers a general civilian to use it, right? So therefore, it's operator independent. Everybody can use it. You don't need any training. It's low cost. And this patch is wearable. It provides a 24/7 monitoring. You can do this measurement anytime, anywhere, right? It gives you comprehensive data. It does not lose any critical information. And most importantly, this device allows you imaging during motion, so you can couple exertion to those diagnosis process. And it's gel-free, so it enhances wearability and does not have this disinfection problem. So this is the vision. I come from a materials background. We can exercise all kinds of hardware device engineering, such as implementing all kinds of sensor modalities. We can learn from the literature, improving the image performance, do all kinds of functional circuit integration, and sometimes we can also apply interventions, apply those stimulation to this human body, right? We work closely with clinicians to do those validation studies to improve the safety, improve the performance, and do all kinds of monitoring facilitation during these procedures. Wearable ultrasound generate lots of data, and data is now the new oil, right? We work with data scientists to make sense out of those continuous data streams. We do data mining to extract those important features from those images, and that allows us to understand those etiology, the disease mechanism better. We can also enhance data quality by developing better imaging algorithms so that our imaging performance is enhanced. We got all those continuous data streams, so that enables us to build those so-called digital twin, so that we can predict those acute diseases before it really happens, and that gives you time to apply those intervention to prevent any disaster outcomes. So finally, I want to conclude by acknowledging my group. I'm learning from my students and postdocs every day, and those are my critical collaborators who provided the support. Without their support, those work can never be done. And also the funding agency, the size of the logo is roughly proportional to the amount of funding I accumulated over the years. So finally, I want to make an announcement that I'm constantly looking for students and postdocs with a background in ultrasound to join my group. Anything, in any aspect, materials, application transducers, hardware circuit design integration, signal processing, imaging algorithm development, and so on and so forth. So this is our campus, this is our library, our lab is somewhere here, and this is the Pacific Ocean. So with that, thank you so much again for your time.
Questions? Okay, we'll start from the back.
Could you please elaborate a little bit more on the way that this technology can be used? You said that it could predict a heart attack earlier than EKG could?
Yes. So this is what a clinician, a clinical collaborator told us. They actually, EKG is electric activity. This ultrasound image is a mechanical activity. So from what I learned from him is that there's a mechanical activity actually shows up earlier than those electric activity, about half an hour earlier. So that allows you, some more time to do like interventions. So that's the take I have. Yeah. Yeah. Obviously I'm not a cardiologist. I'm not a clinician. Yeah, so
Thank you.
good question.
Okay, you mentioned the photoacoustic. So you integrated the laser on the patch.
Yes.
Okay, so because when we do photoacoustic, there's some requirement like the thermal confinement, right? So then, what's the parameter of your laser? So what's the except the wavelength and also the pulse?
Oh, very good question. We have to buy a actual power amplifier. So it's very, very high power, but it's pulsified. Pulsified with a.
So what's the duration?
I think I remember it's a femtosecond, pulse.
Femtosecond. So it's cannot meet the thermal confinement requirement or the stress confinement.
Thermal confinement. I'm not sure. If
So that's the reason we usually use nanosecond pulses.
I see.
Yours is millisecond. So, but when you do quantitative imaging analysis,
Yeah.
so there's some requirements about the photoacoustic. So that's the reason I'm really.
Very, very good question. You know what? I'm not the expert in photoacoustic imaging. This guy, he got a PhD from photoacoustics. And he was the one who introduced me to photoacoustics.
Okay.
Yes. You know what? I can send you the paper. It's all documented in our paper. In terms of the laser specific parameters. Yeah, very good question. Yeah.
Question.
Thank you so much. That was amazing. I had a question about your ability to focus the beam of the ultrasound using the time delay.
Yeah.
Which imaging modalities utilize that technique, and how does that technique affect like the sampling frequency to generate like a beam mode image, for example? Like, can this be used? Do you use that when you're imaging the heart?
Well, good question. For beam mode imaging, we normally use this plane wave or those divergent wave plus compounding. For those there's a phase array imaging, we normally do it with Doppler, color Doppler or spectrum Doppler. Normally spectrum Doppler, because we have to steer the beam to a specific location, right?
Gotcha.
Normally spectrum Doppler, but for beam mode imaging, we don't use it. Beam mode imaging is divergent wave, plane wave.
So this could not be used for.
Yeah, otherwise it's gonna be very low frame rate. Yeah, it's not necessary. Yeah,
Right.
yeah. Very good question.
Okay, over there.
You showed the graph comparing the patch to the cup, and it did follow the general trend, but there were some spikes that didn't match up. What is the significance of that? Like, do you have a certain percentage for how accurate the patch is versus the cup? Is the cup the most accurate form right now?
Very good question. Hey, you know what? Cuff is the non-invasive, I would say the most accurate measurement of blood pressure. But in terms of gold standard, there is only one gold standard. Gold standard is the A line, and it's invasive. And you know what? After talking with those clinicians, they told me A line is not always accurate either. They are artifacts. Cuff also have lots of artifacts in accuracy. That's why sometimes clinicians will have to measure 3 times using cuff and do the average, right? And talking about this mismatch of these 2 modalities, there are many sources of error. For example, just give you a few examples. First, we do those measurements on different arms, right? Put the pressure on this one and the cuff on this one, right? Otherwise, they will interfere with each other, right? And some people will have those discrepancy of blood pressure at different arms. And maybe during measurement, they do different gestures of different arms. That can introduce those spikes in those data, right? That's one thing. Second thing is those measurement even on the same arm, different locations, right? This and I'm sure you know on this arterial tree, the blood pressure is very different. Right? At the distal part, the peak is higher, and the central part, proximal part is the peak is lower, right? So those are the 2 major sources of error for those discrepancies. Yeah, good question.
Thank you very much. This is really cool. I had a quick question. You stated that there's a direct correlation between your peaks and your troughs directly to your blood pressure because that's just the nature of the arterial extension. So, do you see any attenuation to your like peaks and troughs when you do your signal treatment on your raw signal? And if you do, how much does that affect your true blood pressure estimation? Because we do a lot of PPG signal treatment, and when you do a lot of these filtering, you get this attenuation on peak and on the DC baseline. So does that appear in this?
Very, very good question. You know what? I'm a materials engineer. And my student did this data processing. From my understanding, we do this calibration of two values. So you got those distension, right? You got this blood pressure waveform, right? We do calibration on the distal blood pressure, systolic blood pressure and diastolic blood pressure. We calibrate both the top and the bottom. And once you calibrate both, then everything in the middle is lined up. So that's our basic mechanism.
So you calibrate based on your treated signal already, not on any kind of pre-process.
We calibrate the diastolic and systolic using the cuff together, just one time. And then, everything just moves forward.
And do you see the potential for this being able to extract actual arterial stiffness values, so your mechanical properties, like raw mechanical properties?
Yes, we can.
Viscoelastic effect.
Yes. The reason why we have to calibrate both is we can use that to calibrate the arterial stiffness. Alpha is a factor alpha. And some people, this alpha may shift, during, disease, or if you eat, some, food or drinks, or maybe during exercise. It will change. And you know what? It's actually changed much, much smaller than what we expected. So in our, experiment, we showed that even you do those exercise and drink alcohol, coffee, whatever, that will change so small. It's much, much smaller than the FDA regulation, 5 milliliter plus minus 5 million mercury. Yeah. Thank you for the question.
Sorry, go ahead.
Yeah, we can go back to materials. So your zinc oxide, vertically grown zinc oxide nanoarrays that you use for your simulation.
Very good question. So zinc oxide was my PhD work, and I don't work on zinc oxide anymore. This is a PCT, PMNPT. Yeah, and I know you have lots of experience with PCT. Yeah.
These fibers, right? These are fibers.
Yeah, fibers, pillars. Yeah.
How much voltage typically do you apply for getting this 5 to 10 centimeter deep tissue resolution?
How much what?
Voltage do you apply?
20 to 30 volts.
So
Is
for
enough.
each transducer, it's about 1 milliwatt. What is the power per transducer? How much power do you apply?
That part I really don't know. Yeah. The voltage is about 20 to 30 volt, and the current I really don't know the color. Yeah.
E square F, so maybe it'll be about milliwatt.
Yeah, maybe. Yeah.
What are some next steps or improvements for this specific device, if there are any?
And lots of things we have to improve. And I would say the most urgent thing that I'm thinking about is the imaging quality, the resolution contrast. We demonstrated the proof of concept, but I think in order to be clinically valuable, we have to improve it. It does not have to be as good as those clinical ultrasound, right? Because we are talking different use scenarios. Our use scenario is when those clinical equipment are not available. Say, for example, when they're outside the hospital. So we can do those screening, we can do this baseline monitoring, right? But still, there's some room to improve. That's one aspect. Another aspect is those reliability, robustness. So clinical ultrasound device can be used for decades. But our device, we can recycle them for 5 or 10 times. Then you can start to degrade and delamination, so on and so forth. So those are the two, I would say, immediate aspects we can improve. We should improve. Yeah, very good question.
Okay, so let's last one over there.
On your, for the comparison to the currently available ultrasound technology, one of the pros you had on yours was it's a lot cheaper. There was a cost improvement. I was wondering what if you were able to manufacture this at scale, what would you project the price of that being compared to current?
Yeah, that's a very good commercialization question. I get asked it a lot by these investors. So obviously, I would say the value proposition of this technology technology twofold. One fold is what you said. The material, the hardware part, is lower in cost. This cup-based ultrasound equipment in the hospital is like 100K, 200K each, right? Here is much lower, right? Orders of magnitude lower in price. Second thing is a human cost. For this conventional ultrasound equipment, you have to use the operator, which needs a lot of training, right? But here, in our case, we don't need this experienced user. So that part is significant. We can cut them down. Everybody can use it. Yeah. So those are the two value propositions. Yeah. Good question.
One simple question. So so you mentioned the wearables. So one wearable is the goggle. Like the AR, VR devices.
Yes.
Is it possible to use your system to do eye monitoring?
Yeah, people told me about this. Potentially yes, but the thing is for ultrasound, biomedical ultrasound does not penetrate the air. So you have to be in contact with the skin. If it's in contact with skin, then the angle, the modality you can sense is kind of limited, but we can somehow use a lower frequency like the bats, the bats, right? They use ultrasound to navigate, right? I think potentially yes.
Yeah, eye tracking currently is, I think, is a key issue in the wearables.
Yeah. Why do they want to do eye tracking?
That's the attention point. So when you shift your eye, your attention direction will be changed.
Yeah, that's right. Yeah, for the VR, yes. Very good point, yeah.
Okay, I know a lot of you have classes at 10, so let's end the seminar here. Let's thank Dr. Wu again for.
Hey, thank you so much.
I watched the whole seminar.